Hi, in this module, I'm going to cover the basics of linear regression. A story of linear regression begins on January 1st, 1801. Italian astronomer Piazzi looked up at the night sky and discovered something, which he named Ceres. He didn't know what it was it a comet or a planet, but he did make some observations of the location before it was obscured by the sun. The data he collected looked like this. At a particular time, two numbers which represent the location of Ceres in the night sky. So now the big question at the time was when and where was Ceres going to be observed again to re-emerge from behind the sun? All the top astronomers at the time went and tried to analyze this data and figure out the answer. So Carl Friedrich Gauss, famous German mathematician, took Piazzi's data and created a model of Ceres orbits and makes a prediction. This prediction was actually wildly different from all the other predictions that other astronomers made, but in December, Ceres was located and Gauss's prediction was by far the most accurate. So now there's an interesting story here. Gauss was actually very secretive about what his method was, and in 1805, the French mathematician Liang was actually the first to publish the method before Gauss could publish it in 1809, even though Gauss had this method back in 1795. The method here is none other than least squares linear regression, which is the topic of this module. So here is the framework. So we are given some training data, which consists of a set of examples. Each example consists of an input x and an output y. So 1, 1, 2, 3, 4, 3. And we can visualize these examples on a 2D plot here, plotting y, the output, against x, the input. So here is 1, 1, here is 2, 3, and here is 4, 3. So what we want to do is take this data, have a learning algorithm, produce a predictor f. And the predictor in this case is, let's say, a line. Okay, and what the predictor allows us to do is to take new inputs, such as this 3 here, and send it through and produce an output, 2.71, corresponding to this point on this line here. And there are 3 design decisions that we need to make to flesh out this framework. First, what are the possible predictors that the learning algorithm is allowed to output? Is it only lines or is it curves as well? This is a question of what is the hypothesis class. Second question, how good is a predictor? And the answer is going to be framed in terms of determining a loss function that judges each individual predictor in the hypothesis class. And finally, how do we actually compute the best predictor? There are a lot of predictors there. And even if we have the loss function, how do we go searching for them? And this is going to be the question of the optimization algorithm. So this is a recipe that we're going to see over and over again. And it's kind of like a build your own learning algorithm. So we're going to start with the first question. What is a hypothesis class? So here is that predictor that we were looking at. F of x equals 1 plus 0.57x. And that corresponds to this red line. And here's another one. Here's a purple predictor, which has an intercept of 2 and a slope of 0.2. And in general, you can consider predictors of the following form: f of x equals w1 plus w2 of x for arbitrary w1, which is the intercept, and w2, which is the slope. So now we're going to generalize this using vector notation. So let's take w1 and w2 and pack them up together into a vector, which we will call w. This is called a wave vector. And we're also going to define a feature extractor, also known as a feature map, phi. So phi is going to take an arbitrary input x and return the vector 1, comma x, at least in this case. And 1, comma x is going to be known as the feature vector. So now we can simply rewrite this equation up here in vector notation. So we're going to write f sub w to denote that this predictor depends on the weights of a particular input x is equal to w dot phi of x. And this w dot phi of x, which we'll see over and over again, is called the score. Okay, so here's an example. If you stick in 3 into this predictor, then what we're doing is taking the weight vector and dotting it with the feature vector applied to 3. And remember, the definition of feature vector is 1 comma x, so that's 1 comma 3 here. And if you take the dot product, 1 times 1 plus 0.57 times 3, that gives you 2.71. So now, finally, the hypothesis class is defined as the set script f is the set of all predictors f sub w, where w can be an arbitrary intercept and slope. W is an arbitrary vector. Okay, so that defines our hypothesis class that we're going to be working with. So now let's turn to the second design decision. How good is a predictor? So let's take our predictor that we're looking at, the red one, and let's look at some training data. So this is the training data that we had before. Let's plot the predictor and the 3 data points. This one, the 2, 3, and 4, 3. So intuitively, how good is a predictor is how good it fits the training data. And we're going to quantify that by measuring the distance between the prediction and a target. This difference is called the residual. So we're going to measure the residual for each of our points, and we're going to take that into account. So formally, we're going to define a loss function, which is a function of an example xy and a particular weight vector, and that's going to be equal to the prediction f of x minus the target y, so that's the residual here, and I'm going to square it. So that is called the squared loss. So as a side, you could also take the absolute value here, which gives you the absolute deviation loss, but we're going to stick with the squared loss for mathematical convenience. So on these 3 examples, we can compute the loss. So we take 1, 1, and the weight vector, we dot them together, that's the prediction. You subtract off the target, and that is, and square it, and that gives you 0.32. Second example is 2, 3, and the third example is 4, 3. Each one gives you a loss function, which corresponds to the square of the length of these dashed lines. So now we can define the training loss of a particular weight vector to be simply the average over the losses. So formally, this is going to be a sum over all the examples in our training set, so these, and of the loss function of a particular example with respect to that weight vector. And then finally, we're going to just divide by the number of points in the training set to normalize. So in this example, we just average these 3 numbers and we get 0.3. Okay, so that is how we define the squared loss and the training loss in terms of the squared loss. So here is the training loss as we had from the previous slide, and we can visualize this. So for every single weight vector, we can stick it in and get out a number. So fortunately, W is only 2-dimensional here, so we can plot this actually. So here is the plot, W1, W2, and every point here gives you a training loss on the z-axis. So red here denotes high loss, blue here denotes low loss, and so it's natural to think about how you would find the point here with the minimum training loss. And that's captured mathematically as minimum over W of train loss of W. So this is the optimization problem that we want to solve. So now the third question is, how do you compute the best? So fortunately, we already have our well-defined goal. We want to find the weight vector that minimizes the training loss. And we're going to adopt a very simple strategy called follow your nose. Okay, so you start at a particular W, and then you sniff around, and then you just move in the direction that seems like it's going to reduce your loss the most. More mathematically, we're going to define the gradient as the direction that increases the training loss the most. And importantly, we want to go in the opposite direction because we want to decrease the training loss, not increase it. So pictorially, what the follow node strategy or gradient descent is going to look like is you're going to start at some w, and then you're going to follow the gradient, and you're going to end up here, and then you're going to compute the gradient, you're going to end up here, and you might bounce around a bit, but hopefully you'll decrease the loss on average over time. Okay, so here's the pseudocode for gradient descent. So we initialize w to be something, let's say zeros for simplicity, and then we're going to repeat big T times. Big T is the number of epochs. And what we're going to do is we're going to take our old value of the wave vector, and we're going to subtract out some eta, which is called the step size, which we'll get into a little bit later. So here's the step size times the gradient. So grad of retraining loss of w. So that's called the gradient here. Okay, so that's it. There's 3 lines and really only 1 line that's of interest here. And that's all there is to gradient descent. Okay, so at least at an abstract level. So all that remains to do is to actually compute the gradient. So remember, here is our objective function. Train loss is the average over the individual losses, which I've expanded the squared loss right now, but gradient descent is actually much more general than just the square loss or even machine learning. And now we just need to compute the gradient. And if you remember your calculus, here's how you do it. So the gradient with respect to w of the train loss of w. So remember, there's a lot of symbols here, but we are differentiating with respect to w, not x, not y, not v. And this is going to be equal to the gradient of this expression. This is just a constant, so the gradient can be pushed inside. And this is a sum. The gradient can be pushed inside a sum linearity. So this is a sum over the training set again. And then, so now the interesting thing happens. So here is something squared. The gradient of something squared, you bring down the 2, and then you have the same something, which is, you remember, the residual, times the gradient of what's inside here. And what's inside here is w dot phi of x. Phi of x is a constant, y is a constant, so the gradient of that residual is just phi of x. And so notice that there's something interesting I want to point out here, which is that the gradient can be expressed as the residual times the feature vector, where the residual is the prediction minus the target. So intuitively, you can think about if the prediction is equal to target, then the gradient is 0, so nothing will happen. And if the prediction is not equal to target, then the gradient will be in the direction that sends the prediction away from the target. And remember, we're always minimizing, so we're subtracting that off, in which will move the weights in the right direction. Okay, so let's walk through the gradient descent for our example here. So here's a training example again. Here is the expression for the gradient that we just computed on the previous slide. And here's the gradient update where I've taken the liberty of just substituting the step size to be just 0.1, just for simplicity. Okay, so we start with w equals 0, 0. And then what we're going to do is plug in 0, 0 into this training loss expression, this somewhat nasty looking thing. And that is this. This is just simply the average, 3 examples, 1 over 3. Here's the first example, here's the second example, here's the third example. Each example consists of dot product, the prediction minus target, times the feature vector of that example. So I'll let you go through the details here, but if you do the math, you get minus 4.67, minus 12.67. You multiply by the step size, and you get this weight. Okay, so now the second iteration, you're going to take this wave vector, stick it into this expression all over again. You compute a new gradient, and then you subtract that gradient times 0.1 from this wave vector, and you're going to get a new wave vector. And then you keep on repeating and repeating. So after maybe 200 iterations, you're going to end up with something like this. And something interesting happens. If you're lucky, the gradient at the end will be 0. So what does 0 mean? So 0, if you subtract out 0, you get the same thing. So means that gradient descent has converged. By subtracting off the gradient, you're not going to move anywhere, and so you might as well just stop. And the stopping point is this wave vector 1, 0.57, which is indeed the red classifier. So just to concretize this even more, let's do gradient descent in Python. Okay, so I'm going to pull up a terminal here. So in practice, you probably wouldn't implement gradient descent from scratch, except for if you're just trying to learn about gradient descent. But for pedagogical purposes, let me do this. Okay, so I'm going to do this in a kind of very bare bones way. So I'm going to use NumPy rather than PyTorch or something that can do gradients for you. First, I'm going to define our training examples as 1, 1, 2, 3, and 4, 3. I believe those are the training examples. Let me just double check over here. 1, 1, 2, 3, 4, 3. Okay, so now I have to define a feature vector of x, which is, remember, is 1x. So this is just a NumPy array. I'm going to initialize the wave vector with, let's call this initial wave vector. And this is just going to be an all zeros vector of dimension 2, which is going to match dimensionality of phi. Okay, so now I need to define the training loss. Training loss takes a wave vector, and I'm going to actually go to the previous slide here, and it's just basically copying down math and turning it into code. So this is 1 over the number of training examples times the sum, and the sum is over for all training examples xy and training examples. And for each one, I'm going to do w dot p of x. It's really literally the same thing, minus y. And I'm going to take this expression, the residual, and I'm going to square it. Okay, so let's make this a little bit bigger. Okay, so that's the training loss. Okay, now I need to take the gradient. So I'm going to cheat a little bit and just copy that down here and edit it. So the gradient of the training loss is going to be 2 times the residual times p of x. Okay, so that's it for the training loss. Okay, so now I'm going to implement gradient descent. So I'm going to do it this way, actually. So gradient descent, like I alluded to before, is actually a general purpose optimization. So all it needs is a function, gradient access to that function, and an initial wave vector, and it's ready to go. Okay, so I'm going to initialize w to the initial wave vector, and then I'm going to, let's say, eta to 0.1 for a number of iterations, t in range of, let's just say, I don't know, 500, just for fun. I'm going to evaluate the function at w. I'm going to evaluate the gradient. And I'm just going to do the one-line thing of subtracting out eta times the gradient from the existing wave vector and setting it to the new wave vector. And I'm going to print out where I am. So epoch t, w equals w, f of w equals the value. And let's do the gradient just for fun. So gradient f equals the gradient. Okay. Okay, so now I just need to call gradient descent with what function am I optimizing? The train loss. The gradient of the train loss is the gradient of the train loss, and the initial wave vector. Okay, so that's all I have, and let's actually just run it. Gradient descent. So we see here that in epoch 0, the wave vector is something, and the function value is something, gradient something, and over time, the function value is going to decrease, which is a good sign. The gradient of f is going to start becoming more 0. And the weight vectors are now converging to 1, 0.57 as advertised. So I will declare this program working. Let's just to kind of summarize what we did here. So I want to set this up as follows. So here is the optimization problem, which is how you have the training example, the feature vectors, the loss and gradient, and so on. And this is kind of a specification of what the problem we want to solve is. And then down here, we have the optimization algorithm. And we're going to be doing this a few times throughout the course, drawing kind of modules where we can separate the optimization problem from the optimization algorithm. Notice that the optimization algorithm, again, doesn't depend on anything relating to machine learning at all. And the optimization problem doesn't say anything about how you solve it. So the decoupling this what from the how, I think, is a really important theme. Okay, so that was gradient descent in code. And let's summarize now. So in summary, we take training data, we have a learning algorithm that produces a predictor that can produce new predictions on new inputs. And there are 3 design decisions for build your own learning algorithm. Which predictors are possible? That is a question of hypothesis class. And we consider linear functions here, where the function is simply w.phi of x with a particular feature map, 1, x. You could imagine other things. We'll see other things later, nonlinear features and even neural networks. But it's still the question of what is the hypothesis class. How good is a predictor? That's a question of what is the loss function. For regression, we looked at the squared loss. Later for classification, we're going to look at the hinge loss and the 0-1 loss. But this is orthogonal. For neural networks, we can also look at the hinge loss or the square loss or any of the losses. And finally, how do we compute the best predictor? This is a question of what is the optimization algorithm. And for this, we introduce gradient descent, which is this lovely, simple, and very effective algorithm for optimization. So that concludes this module.